Ever heard of a physics concept so fundamental it basically dictates how the universe is structured? Well, buckle up because today we're taking a deep dive into Wolfgang Pauli's exclusion principle.
And it's a wild ride, let me tell you,
We're going to trace its origins, unpack its mind-boggling implications,
which there are many.
and discover why, even after winning a Nobel Prize for it, Pauli still felt like we were just scratching the
Oh,
surface.
absolutely. Just scratching the surface. What's so fascinating about the exclusion principle is how it emerged from this whirlwind of ideas that were swirling around in the 1920s. Picture this. A young Pauli, just a student at the time, right in the thick of a physics revolution brewing in Munich.
So it's less of a lone genius eureka moment and more like he was standing on the shoulders of giants.
Exactly. He was surrounded by these incredible minds, like his professor, Arnold Sommerfeld, who was a giant in his own right. Sommerfeld had this really elegant way of looking for numerical patterns and spectral lines, those unique fingerprints atoms leave when they emit light.
It sounds like Sommerfeld really emphasized the beauty of math underpinning it all.
Absolutely, the elegance of it all. Now, contrast that with Niels Bohr, who at the time was, well, he was rocking the physics world with his quantum model of the atom. It was radical.
hmm
So imagine young Pauli, caught between these two titans of physics, each with their own distinct perspective on quantum theory.
That must have been both exhilarating and a little intimidating for a young physicist trying to find his footing.
Absolutely. And these contrasting viewpoints, they actually fed into Pauli's journey toward the exclusion principle. See, Bohr himself was wrestling with this question that became a sort of seed for Pauli's later work. Why don't all the electrons in an atom just crowd into the lowest energy state?
That's a great question. Because it's kind of like, in a crowded room, everyone wants to be closest to the heater. But in an atom, there's some hidden rule book saying, nope, only one electron allowed per energy level. What's the deal with that?
Precisely. And this question, it followed Pauli back to his own lab in Hamburg, where he was grappling with another puzzle, the anomalous Zeeman effect. Essentially, when atoms were placed in a magnetic field, the way their spectral lines split just didn't quite fit with the existing models.
So it was like the universe was sending mixed signals and Pauli was trying to decode them.
Exactly. And through this decoding, he started to realize that there was something fundamental about the electron itself, something that was still missing from our understanding. He even called it a classically non-describable two-valuedness. It was like the electron had this secret characteristic nobody knew about.
Okay, two-valuedness. That sounds intriguing, but maybe we can unpack that a bit. What did he actually mean by that?
Okay, so imagine this. Back then, we thought of electrons mainly as particles orbiting the nucleus, like planets around a star, right? But Pauli's work, along with a crucial insight from physicist Edmund Stoner, started to reveal that this picture was incomplete. Stoner noticed this link between the number of energy levels in alkali metals and the stable electron configurations of noble gases.
So like a hidden pattern connecting these seemingly different elements.
Exactly. And this pattern hinted at a deeper principle governing how electrons behave. This brings us to what we now know as the Pauli exclusion principle. The simplest way to think about it is this. Electrons are like guests at a very, very exclusive hotel, where each electron needs its own unique room.
And this isn't your typical hotel room, is it? It's defined by something a bit more, dot quantum.
You got it. Each room is defined by a set of 4 quantum numbers, kind of like the room number, floor, building, wing, all of those identifiers combined. Pauli's exclusion principle essentially says, no two electrons can have the same exact room. Only one electron is allowed per unique set of these quantum numbers.
So this quantum hotel is full of electrons, each with their own unique address. That's a pretty cool way to visualize it. But how does this principle actually play out in the real world? What's the significance of all these electrons having their own rooms?
That's where things get really interesting. This simple principle, one electron per unique quantum state, it underpins the entire structure of the periodic table.
Wait, the periodic table? That iconic chart elements we all saw in chemistry class?
The very same. Pauli's exclusion principle, it's the reason the periodic table isn't just this random jumble of elements. Let's try to help our listener visualize this. So imagine you're building atoms, right? And you're adding electrons one by one.
Okay, I'm with you so far.
Now, the first few electrons, they're going to occupy the lowest energy levels, those rooms closest to the nucleus.
Makes sense. Those prime real estate rooms, they'd fill up first.
Exactly. But here's the catch. Because of the exclusion principle, once an energy level is full, Any new electrons, well, they have to go into higher energy levels further away from the nucleus.
So it's like each element is built by stacking these electron floors on top of each other with the exclusion principle acting as the, I don't know, the building code.
A perfect analogy. And this building code, it dictates everything from an element's reactivity to its ability to bond with other elements. Take those noble gases we talked about earlier. They have their outermost electron floors completely filled.
So they're like those folks who build a house way out in the country because they just want peace and quiet, no need for interaction.
Precisely. Their electron configurations, they make them very stable and unreactive. And here's the thing, this principle, it goes beyond just electrons. As it turns out, Pauli's exclusion principle hinted at something much deeper about the universe, a fundamental connection between a particle's spin and its behavior.
Hold on, back up a bit. We're talking about more than just electrons now.
Absolutely. Remember that two-valuedness we mentioned earlier? Well, it turns out that electrons, they have this intrinsic property called spin, which you can kind of think of like a tiny internal magnet pointing either up or down.
So it's like our electrons in their quantum hotel rooms also have a secret switch that can be flipped one of two ways.
Exactly. And it's this spin that provides that extra quantum number needed to completely define an electron's state. And here's the really mind-blowing part. Pauli's exclusion principle, which started with electrons, it applies to a whole class of particles called fermions. And what do they all have in common? They share this property of having half-integer spin.
Okay, you're going a bit deep into the quantum weeds for me here. But what I'm gathering is that this principle, something discovered while trying to understand atoms, ended up revealing something very fundamental about the very fabric of the universe.
You got it. And it took another visionary physicist, Paul Dirac, to really connect the dots. Dirac was trying to, well, he was busy trying to reconcile quantum mechanics with Einstein's theory of relativity. And in doing so, he stumbled upon something truly remarkable.
Dirac, the man who predicted antimatter, right. But wasn't his work completely separate from Pauli's?
Not entirely. See, Dirac's equations, while revolutionary, initially predicted these strange states of negative energy. It was like physics was suggesting the universe could have negative mass or even negative time, which obviously...
Sounds like a recipe for a cosmic accounting error.
You could say that. But then Dirac had this flash of insight. What if those negative energy states, what if they were already filled with electrons?
Like our quantum hotel, but with a basement level that's already completely booked.
Exactly. And because of Pauli's exclusion principle, no other electrons could occupy those states. But, and here's the kicker, what if there was a hole in this sea of negative energy electrons?
A vacancy in the quantum basement? What would that even look like?
Well, Dirac realized that this hole would actually behave like a particle with positive energy and positive charge. In other words, the opposite of an electron. And that, my friend, is how the concept of antimatter was born.
So Pauli's exclusion principle, in this roundabout way, led to the prediction and eventual discovery of antimatter. That's incredible.
It really is.
Yeah.
It's a testament to how interconnected these fundamental concepts in physics really are.
It's mind-blowing to think that a principle discovered while trying to make sense of atoms ended up predicting something as radical as antimatter. It really highlights how interconnected these seemingly abstract physics concepts can be.
It really does. And, for Pauli, this was just the tip of the iceberg. Even after he won the Nobel Prize for the exclusion principle, he knew there were still deeper mysteries hidden beneath the surface.
So even with the Nobel Prize, he wasn't content to just rest on his laurels.
Not at all. In his Nobel lecture, he actually openly acknowledged the limitations of existing theories at the time.
Oh, really? What did he say?
Well, he pointed to those pesky infinities that kept cropping up in calculations.
Yeah, those infinities.
A sure sign that something fundamental was still missing.
Those infinities, they sound like a real headache for physicists. What did he make of them?
He saw them as a challenge, you see. For Pauli, these infinities weren't roadblocks. He saw them more as guideposts, hints pointing toward a more fundamental theory of physics, one that could naturally explain things like the constants of nature, why the electromagnetic force is the strength it is and things like that.
So it's like he was saying, okay, we've come a long way, but the universe still has a few tricks up its sleeve.
Exactly. He was particularly perplexed by what he called the atomistic nature of electric charge, the fact that charge always seems to come in these tiny, discrete packets, like electrons and quarks. He believed a truly fundamental theory would have to explain why charge was quantized in this way.
It's incredible to think that even with all the progress we've made in physics, we still have these fundamental questions that remain unanswered. It's a bit humbling, really.
It is.
Mhm.
But it's also incredibly exciting, right?
Yeah.
I mean, it means there's still so much more to discover, so many more layers to peel back in our understanding of the universe. Who knows what mind-blowing revelations await us?
This whole deep dive has really got my gears turning. If the exclusion principle is as fundamental as you say, I can't help but wonder, what would happen if it were even slightly different? Like, what if instead of just one electron per quantum state, you could fit two, three, or even an unlimited number?
Yeah, that's a truly fascinating thought experiment.
Yeah.
Would we even have atoms as we know them? Would matter behave in completely different ways? It really makes you appreciate the delicate balance of the universe we live in.
It certainly does. Well, I think we've given our listeners plenty to ponder today. The exclusion principle, this seemingly simple concept, has led us on a journey from the structure of atoms to the existence of antimatter, and even to the very edge of our current understanding of the universe.
And the best part is, this is just the beginning. As we continue to explore the quantum world, who knows what other mysteries we'll uncover.
Until next time, keep asking those what if questions. You never know where they might lead you.